Newton's first law states that an object in motion will stay in motion and an object at rest will remain at rest unless an unbalanced force acts upon it. If an outside force acts on an object, the object is no longer in equilibrium, or in a state where the net forces acting upon the object are equal to zero. An object's property to resist changes in its motion is called its inertia. Inertia is proportional to mass. The more massive an object, the more inertia it has, and the more force is required to get the object moving, or stop it if it's already moving. Izzy is an object at rest when she is standing still, and she will continue to stand still unless something happens to her. If a really strong wind blows or a careless friend accidentally runs into her, she would become an object in motion. Izzy is an object in motion when she is skating down the sidewalk. She is moving at a constant velocity, and if there was absolutely no friction or air resistance, she would continue to move at constant velocity forever, or at least until she ran into something or used her brakes to stop herself. In reality, there is a little bit of friction acting on Izzy's rollerblades, which is why she will eventually slow down. This will take a long time because there's not very much friction due to the small surface area of her skate's wheel, but friction is a topic we'll cover more a little bit later. Newton's second law states that acceleration is directly proportional to the net force and inversely proportional to the mass. The net force is in the same direction as the acceleration. In other words, we are given the equation F equals ma, or force equals mass times acceleration. What this means for soccer is that kicking a smaller ball with the same force as a larger ball will result in a greater acceleration of the smaller ball. For this reason, younger kids have smaller soccer balls because it takes less force for the balls to accelerate the same amount as the balls the size that professionally soccer players use. Newton's third law states that for every action there is an equal and opposite reaction. When Rashika runs into the wall, she exerts a force on the wall. The wall exerts the same force in the opposite direction back at her. Because Rashika has a relatively small mass compared to the wall, the force from the wall causes her to accelerate backwards and fall over, whereas Rashika's push on the very massive wall causes it to accelerate at such a small rate that it is not visible. This is similar to how a soccer ball hits a goalpost. The soccer ball will bounce back, but the goal will remain stationary. Possibly it might shake a little bit. However, if two objects of about the same mass collide, such as Izzy and Audrey, then both of them would accelerate away at about the same rate due to the force of the other person. This is very important to understand in contact sports where players often collide.
As Izzy kicks the ball, the path of the projectile is in the shape of a parabolic arc. There are two components of velocity. The horizontal component stays the same throughout the entire projectile path. However, the vertical component, which is the speed of the ball in the y direction, is different. The moment the ball is kicked, gravity tries to slow it down. This decreases the vertical velocity component. Finally, the vertical velocity stops decreasing at the maximum height and reaches zero. Then gravity is pulling it back down and the vertical velocity increases until it reaches the ground. Free fall occurs when Rashika falls off the tightrope. In the first instance, Rashika drops from her tightrope. In the second instance, Rashika projects forward. Regardless of horizontal motion, both instances she experiences the same vertical motion. She should reach the ground at the same time for both. It is also important to note, if two objects are released from the same height, they should theoretically reach the ground at the same time, ignoring air resistance. This is because they experience the same acceleration due to gravity.
Something to keep in mind when talking about motion is your frame of reference. A frame of reference is something you use to define motion when you assume your point of reference or the place of the object you're judging reference from is stationary. If Audrey is moving backwards at a rate of 6 meters per second as she is throwing the ball forwards at a rate of 8 meters per second, from her point of view, the ball has a forward velocity of 8 meters per second. If a person is viewing from the grandstands, they would think it was moving forward at a rate of 2 meters per second. Although we typically wouldn't, you could use the ball as a point of reference and instead say that Audrey was moving backwards at a rate of 14 meters per second.
The law of conservation of energy proves that the total amount of energy stays the same and can only be transformed. As Izzy stands at the top of the hill, all her energy is in the form of potential energy, which is due to her height. After Izzy bows and starts moving down the hill, the potential energy transforms into kinetic energy. The potential energy decreases while the kinetic energy increases. As she reaches the ground, she has no potential energy and only kinetic energy. When she reaches, all her energy is transformed into heat, sound, and other forms.
When Izzy rolls on her rollerblades, she's able to continue rolling for a very long time without any extra effort because there is very little surface area on Izzy's rollerblades wheels that is touching the ground. Also, both are relatively smooth surfaces, meaning that they likely have a low coefficient of friction, or mu. Mu is the ratio of normal force to frictional force. On the flip side, we have the ball rolling across the grass, which slows down rather quickly. The ball has a larger surface area touching the grass, and although the ball is smooth, the grass is very rough, meaning that there is a lot of friction or a high value of mu.